All right, good afternoon again, and here we are for part 2 of, this is lecture 11 on March 30th, 2017, and we are continuing more material from chapter 15 of the Bioreactor Mechanics book, looking at the kinematics of rigid bodies. The kinematics of rigid bodies. So I'm going to continue with this example we have here. We were having some technical issues when we last left, but now those are resolved, and we are recording all right, so we can begin. Okay, we took a short break, got them resolved, and here we are once again. So, if I can manage to not screw up the slideshow. Let's see, go away, and there we go. Okay, so let us keep working at this. So this is our general system here, and so we know that this is a model of the center of the rotation, and then I can determine the angular velocity about c based on the velocity of a, because we do know that one. I know that so let me just label this. I can determine angular velocity about c. The angular velocity about c. In other words, the equivalent angular velocity about c, even though the actual thing is not rotating about c, but at this instant we can treat it as rotating about c. I can determine the equivalent angular velocity about c. Oh, I wrote about twice. Based on the velocity of a. Based on the velocity of a. So in other words, I know that VA is equal to RA times omega. RA times omega, and omega is going to be equal to VA over RA divided by RA, and that is 1.2 meters per second divided by 0.15 meters. I want to use standard units here. Again, this is 150 millimeters from C to point A, and that comes to 8 radians per second. 8 radians per second. Then I can evaluate the velocities of B and D based on a rotation about C. Of B and D based on a rotation about C. Based on a rotation about C. So then I know that here VR, or I can say that VB, I'll just say VB is equal to RB times omega, because I already know the omega, and the omega will be the same thing for everything about point C. So it will be 0.25 meters times our previously calculated velocity, or angular velocity of 8 radians per second. And I will get that VB is equal to 2 meters per second. That VB is equal to 2 meters per second in the I direction. 2 meters per second in the I direction, or to the right. There. Let's see. And then, what else can we do? We can say that, well, I know I can find RD by trigonometry. RD is going to be equal to, because look, it's a 0.15 meter, and this will be 0.15 meter here. So, and it's at a 45-degree angle. So that's just going to be 0.15 meters times the square root of 2. It's Pythagorean, basically. Times the square root of 2, and this is going to be 0.2121 meters. That's R of point D. And then VD is equal to RD times omega which is equal to 0.2121 meters times 8 radians per second squared, or 8 radians per second, sorry. And this will come to 1.697, if I can math properly, meters per second. I could then also break this into components and say that VD is equal to 1.2 I, and they'll be equal just in different directions. The two components will be equal in magnitude because it is at a 45-degree angle, plus 1.2 J meters per second. Meters per second. All right, and that is the basic principle for applying the instantaneous center of velocity.
I got a question.
Yes.
It might be obvious, but how do you know that D is going to be a 45-degree angle?
The question was, how do I know that D is going to be at a 45-degree angle? Well, let's see. If I go back here, actually that would have been given to us, so I guess I didn't label that properly on the diagram. There should have been a line kind of like this to indicate that it was, well, I knew it was perfectly horizontal. D here was perfectly horizontal from A, and since it's the same perfect circle all the way around, I know that that has to be at a 45-degree angle. Does that make sense?
Yeah.
Or in other words, I could have just said that, well, I have a right triangle with two sides of the same length. And what kind of triangle do we call that? Isosceles. 45 degrees if we remember our high school geometry class. Middle school geometry class even. And I'm asking you a lot to remember back to middle school, but okay. So that is how you know that it's a 45-degree angle. And that is the basic idea there. All right, so now I want to move on to talking about a new topic, and that is absolute versus relative acceleration in plane motion. So absolute and relative acceleration in plane motion. Oh, here, let's see. In plane motion. Now here's a question. I put you in a sealed box. Just a simple sealed box, and I ask you. There's no windows in it, and let's just say you have enough air in there for a while. It's a metal box. You cannot penetrate the walls in any way. You cannot sense anything outside the walls. Is there any, if I put you in a sealed room, or and you cannot hear anything, you cannot see anything, maybe there's a light source inside the box with you, so you're not sitting there in the dark. Do you have any way of, actually this is going to be a bit of an aside, so maybe I'll just, when we talk about relative motion, this is what's coming to mind. I want to introduce an interesting topic from relativity, but we won't work through the whole, obviously, all of the essence of relativity, but let me first do a little bit of an aside, something you probably won't find in the textbook, but just something a little bit different. So I put you in a sealed box, and for all you know, you just wake up there one day. Let's not worry about how. So you're in a sealed box, or a sealed room. And for all you know, you could be, again, you cannot, so you're standing in a completely sealed box on all directions. You have a light source so you can at least see around you. And you know what, I tell you in advance, I will give you whatever scientific equipment you want before I seal you in that box. I know it sounds like the premise to a Saw movie, but it's not. Okay, I promise. Anyway, no one's being killed in here. Oh my God. This is a idea of relative motion. So, is there any way that you can tell how fast you're going? Exactly. You could. Some people are suggesting, okay, maybe you could jump in the box. You could jump up, and they're thinking, oh, you would move relative to the box or something like that. But as long as the box is moving at a constant velocity, as long as the box itself is moving at a constant velocity, if you jump up, it'll just keep moving right along with you.
So jump would only work to figure out if it's accelerating.
Exactly. You may be able to use something to determine its acceleration, but you cannot measure velocity. You cannot directly measure velocity. You can use various experiments or tools or estimate or your own senses, whatever, to determine acceleration. There is no way to determine velocity, assuming it's a perfectly sealed box. Now, yes, if you're talking about there was air rushing past and you could hear the wind rushing past or something like that, but if you are in a truly sealed box and you cannot see outside, there is no way to determine velocity. Interestingly enough, is there any way to determine between velocity and acceleration? Or sorry, not velocity and acceleration. Is there any way to distinguish between acceleration and gravity? Is there any way that you can determine the difference between acceleration and gravity? So, you could be, now the simple Occam's razor type solution would be saying, oh, I'm probably on a box in a room sitting on the surface of the Earth. Now, in terms of velocity, we can't determine whether, again, there's no way to determine your absolute velocity. There's really no such thing as absolute velocity. But if you're in that sealed box, I can't tell whether I'm sitting on the surface of the Earth. I can't tell whether I am traveling at a constant velocity in an airplane. I can't tell whether I'm on a train. I can't tell whether I'm going down the highway. I don't know if I'm going, I don't know what speed I'm traveling at, if I'm traveling at any speed whatsoever. I could be at rest. I could be going 10 times the speed of sound. As long as I'm not accelerating, I have no way of determining that. If I'm in a sealed box and I can't see outside and I don't hear, if I can't sense material outside the box, there is no way for me to determine how fast I'm going. It is fundamentally impossible to determine how fast I'm going. And basically what this comes down to is there is no real absolute velocity, really. If something is absolute, that means it's intrinsic. That means you can measure it in its own reference frame. What about acceleration? Well, acceleration is different. Acceleration can be directly measured. For example, with an accelerometer. Now, yes, you could measure your velocity in the previous problem. You could try to cheat and say something like, oh, I'm using a GPS device or something like that. But in that case, you're relying on radio waves that are coming from outside the box. I'm talking about something that you could determine just without using any matter outside the box.
I wouldn't get a signal that way either. You use
Uh-huh.
GPS, sealed box.
Yeah, I'm saying it's a perfectly sealed box, even to EM radiation, everything. Nothing gets in the box, nothing gets out of the box. It's a perfectly sealed box. But acceleration can be directly measured. However, it cannot be distinguished from gravity. So let's talk about that. Now, yes, I could use basic logic and say I am most likely sitting on the Earth's surface or something like that. But let's say I am standing in that box and I'm in the box and I step on I have a scale in there, and I step on the scale and I realize that my reading is 1/6 of my normal weight. Say weight naught is my normal weight. Huh? There'd be two different options. I can think of many different options that might produce this. There are two distinct possibilities, actually. If we are pure, I'm only experiencing a vertical force. One option is that I'm on the Earth. Maybe I'm on the Earth. However, maybe I am accelerating. Gravity is pulling downward, but maybe I am accelerating. I don't know. Actually, a good way to do it would be something like this. Maybe there is a rocket here on the bottom of the box, on the top of the box or something, accelerating downward at an acceleration equal to 7/6 g, and I am actually on the roof of the box. And I don't know it. I will know it quickly enough when I hit the ground. But, and then gravity is pulling me down. With one weight is just mg.
That seems unnecessarily complicated.
Well, it could be, that would be a way to do it.
Couldn't you also just do it like sort of like whenever you're in an elevator that's descending or something?
You could do something like a descending elevator, I suppose. That might be another way to do it, but I like this idea better. This is more fun. Or I could be sitting on the surface of the moon. I could be just standing, the box could be on the moon.
Because my teacher somehow was able to transport us to the moon.
Yeah, it's student funds. We use the money for lunar transport for a science experiment. That's a reasonable use of money, or of state money, right? Anyway, so you could just be sitting on the moon. You can tell it's the moon by the craters. Anyway, so you could be sitting on the moon for all you know. There is no way fundamentally to distinguish between gravity and acceleration. Gravity really is just acceleration. That's all it is. And you can study more up on the theory of relativity, and that really is one of the fundamental bases of it, the theory of special relativity. And I would encourage you to look that up. The math is not actually that complicated, and it's something you can actually get through. Just the math for special relativity is actually less than the math you need for this course, so it's really not that bad. But I always thought this was kind of cool, that you cannot measure absolute velocity. However, you can measure acceleration. It is something that actually has a meaning. You can measure the, even if it was a relatively slight acceleration, I could measure it based off of, the strength, or a very simple way. If I wanted to measure acceleration, say side to side, a very simple way I could do it would be to use a plumb bob. So I have like a protractor type thing, and then a plumb bob. And if this thing is accelerating to a certain degree, the plumb bob, basically this would just be a long string with a very heavy weight at the end. And then under acceleration, this thing will tilt at a certain angle. And I could use some trigonometry and some simple math to calculate what direction, to what amount I'm accelerating. Anyway, so I always thought that was kind of cool. And in fact, actually, I don't think they still use them, but I know some of the original seatbelt designs, like some older style seatbelt designs, actually use something like this. So they have like a so the trick with a seatbelt, like with most seatbelts, you want a seatbelt. You ever notice like how when you are, have you ever actually played with a seatbelt and realized it's actually kind of mechanically designed to a certain ingenious level, if you actually think about it, in the sense that like you can even if you're sitting there, like on a modern seatbelt in a car, you can pull it, it'll pull back, but you can stretch it. As long as you put a small amount of force on it, it won't click. It won't resist the pull. It will come freely. But the moment you try to jerk on it or apply a very large force, then it will stop. Then it will not allow you to pull the seatbelt forward any further. And there was actually if I remember correctly, at one time there was actually a type of seatbelt design that used kind of a pendulum type thing. And so there would be like a pendulum on a weight, and when it tilted back more than, and this pendulum would only be tilted if the forward or backward acceleration were sufficiently large, and there was a mechanism that this motion of this pendulum would then be transformed into a clamping force on the seatbelt. So in other words, the clamp would only activate when the car was heavily braking or accelerating. So kind of an ingenious little device.
More complicated than just the force one.
Well, I'm not sure how that force one works. I'd have to look into the...
Inertial belts.
Huh?
I think they're called
Inertial belts? Yeah, that sounds about right. But yes, so there is fundamentally no way to tell between acceleration and gravity. Anyway, kind of neat to know. But let's talk about absolute and relative acceleration in plane motion. I like the idea of the box being rocketing toward the ground. Brings back memories of Kerbal Space Program. When you're testing your rocket and It goes wrong, and the rocket just slowly starts tipping over and pointing toward the ground, and you know everything's, well, screwed up at that case. Everything's gone full foobar at that point. So absolute and relative acceleration in plane motion. And you try to tilt it back up, and you apply the nav ball commands, and it just keeps tilting further and further and further, and the solid rocket boosters are still going, and before you know it, it's blaring all its rockets full force straight toward the ground, and you know somebody's going to die. Anyway, that has well, something to do with dynamics, so that's okay. Okay, so let's talk about this. Let us look at acceleration. I'm going to do the same kind of thing where I broke up a motion into both a translation and a rotation about a point. So I'm going to draw a potato 3 times, just as I am wont to do. All right, so we're going to have points A and B in all of these. A and B, A and B, A and B, and A and B. And again, I will say that plane motion is equal to rotation plus translation. Is equal to rotation plus translation. Plus a translation. So initially this thing had we had just arbitrary velocities at A and B. So some VA and some VB. Actually, let me say, not velocities here, let me say acceleration, sorry about that. Let's say point A is accelerating with AA, and point B is accelerating with AB here. So we're going to look at accelerations here rather than velocities. And so, oh, you know what? I probably want to have this the other way, translation plus rotation. So let me call this translation with A and rotation about A. Translation with A, or let's just say with A plus rotation about A. All right, so in the translation with A, and I would want to put it in the same direction as the original acceleration AA here. So I would have AA, the same AA, AA and AA here. And then I would have some amount of rotation here. And let's see. So about A, I would have my omega k, some amount of rotation. But then I would also have an alpha k, a rotational acceleration about A, and then I would have a translational acceleration as well. Some sort of translational acceleration. This would be something like this here. Let me see this. B with respect to A. So this would be here. Maybe this here would be A of B with respect to A here. Oh, yes, this would be A of B with respect to A tangential. A of B with respect to A tangential. And A of B with respect to A normal. A of the acceleration of B with respect to A normal or radial. Normal. And then these two would form the components of the overall acceleration of B with respect to A. Here. And then we'd have a radius from A to B. And we'll go through some of the math of this. and this here would be the r, the radius from B to A, or from A to B, I should say. All right, so here, if I were to draw out the acceleration triangle, if I were to take that out of this, the acceleration triangle, or diagram, I might say better, I would have the acceleration of B, I would have the overall acceleration of B, and this would have the acceleration of A, components acceleration of A, and then components, and then as well, the acceleration of B with respect to A. But then the acceleration of B with respect to A would itself be made of two components. Let me put this over here. Acceleration of B with respect to A. But then the acceleration of B with respect to A would be itself made of two components, the tangential and the normal component. And that's what I was trying to squeeze onto the other diagram. So the tangential and the normal component. And normal component. And so then let's work through some math from this, some of the math of this. So the absolute velocity, or the absolute acceleration of the particle B, the absolute acceleration, if I can write, of a particle B is going to be AB is equal to AA plus the acceleration of B with respect to A, B with respect to A. And then, so this is the relative acceleration. So the relative acceleration is the relative acceleration ABA associated with rotation, associated with the rotation A, about A. A includes components, or includes tangential and normal components. Tangential and normal components and these are A of B with respect to A, tangential is alpha K crossed into RBA, RB with respect to A, or which is simply equal to, if I was looking at this is the vector form, or if I just wanted the magnitude, B with respect to A, I would say it is simply R alpha. And then the normal component, acceleration of B with respect to A, vector form, normal, is equal to negative omega squared RBA, and where this, again, where RBA is the radius, or the vector, from point A to point B. From point A to point B, or if I was talking more about, if I just wanted the magnitude and not the vector form, I could say that, actually this should have a tangential on it, sorry. ABA normal, if I was just talking about components, or if I was just talking about magnitudes, would simply be equal to R omega squared. Simply be equal to R omega squared. All right, any questions on that theory? Fun the bun, right? Yes, oh, so much fun, yes. R omega squared. Okay. So let's next discuss, let's continue discussing absolute and relative velocity in plane motion. So I'm going to work through that same, what we've looked at a couple times previously, the sort of, the double piston with the rod between its system. So let's go back to that same system here. And this is useful because we confine motion to a simple system that one component can only move in one direction, or one piece can only move in one direction, and the other can only move in the other direction. And here, so say this is B and this is A here, and let's connect them with a rod from A to B. It's the same kind of thing, and I would have the same theta here as I did before. Let's say this is has a length L. Now, instead of having instead of looking at the velocity at an instant, let us look at the acceleration at a particular instant. So instead of having VB, I'm now going to have AB. And instead of having VA, I'm now going to have AA, which you may feel like you need at this point in the class. And this is, again, at a certain angle theta at one particular instant, angle theta. Theta is the angle between the vertical and the angle of the rod at some given instant. So let's say we have, and I'll do the same kind of thing where I look at plane motion, and plane motion is a summation of translation and rotation. So I'm just going to draw this as a line here for actually no, I'll keep it to what I was. But I'll just leave off the supports and look only at the rod in this case. Make the drawing a little bit simpler. And so again, I have A and B, B and A. And so again, I can say that plane motion, so we'll keep coming back to this, equals the summation of a translation about A, or a translation with A, plus a rotation about A. Plus a rotation, let me put that over here, derp. Plus rotation about A. I don't like how this potato looks, so let me just like that, a little bit better. B and A here. So the translation with A would look like this. I would have an acceleration of A, so AA and AA on both of them. If the whole thing were just moving, accelerating horizontally right along with A, and then I would have some sort of other acceleration there. And let's see. Here, I could have a. Now, in this particular case, I don't know exactly. Let me say that I could say that this is accelerating downward, but I could also say that it's going upward or something like that. Maybe I don't exactly know which direction it's going. So here, actually, you know what? I think I'll trim this diagram a bit. I'll keep it just as I had it. So I would have A. This would be fixed. Then there would be both an omega and an alpha going on this end. So maybe I had omega and an alpha here. And then I would have two relative accelerations. So this is, so I would have the acceleration of B with respect to A, tangential, or sorry, normal in this direction, or centripetal if you prefer. And this would be the acceleration of B with respect to A, tangential here. All right. So the basic equation here, though, would be, well, the acceleration of b, very similar to the previous one. The absolute acceleration of b is going to be equal to the acceleration of a plus the acceleration of b with respect to a. However, the acceleration of b with respect to a is the summation of these two. So this is so ab then would be equal to the acceleration of a plus the acceleration of b with respect to a, its tangential component, plus the acceleration of b with respect to a, its normal or centripetal component. And that would be our guiding equation here. And that would be the basic idea. Let's see. Now, what if in that system, what if in this system, the previous system, I know, or let's say I have AA and VA, and VA, I want to determine AB and alpha, the angular acceleration. Okay. So let's see here. Let's take a look at this. Well, the vector will depend on the direction or sense of AA, AA, and the relative magnitudes of AA and the normal component. AA and A of B with respect to A normal component. And we must also know the angular velocity omega. We also need to know the angular velocity omega. Okay? And so if I want to break this down into components, well, I could look at the x and y components. So x components, well, 0 would be equal to AA plus L omega squared times sine theta minus L times alpha times the cosine of theta. And then if I looked at the y components, and this would all come from doing a diagram of all of these accelerations here. Actually, let me do that before I, before I do this, let me actually draw out a diagram of all the accelerations. I think it's going to make a bit more sense if I do that before I start working through these equations. So let me draw out a diagram here before I start doing a bunch of equations that don't make any sense. I would have AA here, it would be horizontal, and I would have AB pointing down. Then at a certain angle theta, and this theta would be the same theta that the rod itself is hanging at, or is positioned at an instant. At a certain angle theta, this would be the normal component. This would be the acceleration of B with respect to A, the normal component, and then I would have the tangential component here, completing our acceleration diagram. Acceleration of B with respect to A, tangential here. And so I know that AB is equal basically to, I could basically do a summation of forces in the x and y direction, or a summation of accelerations in the x and y direction. So I could effectively do a AB here. Again, so I could write these in terms of the x and y equations. So I can say that 0 is equal to AA plus L omega squared sine phi, theta, not phi, minus L alpha times the cosine of theta, times the cosine of theta here. Then I can say, so this is the x components, AA L omega squared sine phi. That's looking at the omega, this one here, and then L alpha cosine theta. And then the y component, I can say that negative, well actually no, I should just say that the x component, the AB has no x component. That's why we're doing that's why we have 0 here. But for here, for the y components, for a balance of y's, I would say that negative AB is equal to negative L omega squared cosine theta, omega squared cosine theta minus L alpha sine theta. L alpha sine theta. And what I'm doing here fundamentally is transforming the omegas, transforming these into alphas and omegas. And then I would want to take these and solve for AB and alpha. AB and alpha. So let's say I did that. Well, I know that XA, so let's say I want AB, or AA and AB. Well, I know that XA equals L sine theta. That's just a geometric relationship. And YB is L cosine theta. Then VA is going to be equal to X dot A, which is equal to L times theta dot times cosine theta, or simply L omega cosine theta. L omega is theta dot cosine theta, and VB equals Y dot B and then which is then equal to negative L theta dot sine theta, which is equal to negative L omega times the sine of theta. L omega sine of theta. Great. And also, then AA is equal to X double dot A, which will be equal to negative L theta dot squared times sine theta plus L omega double dot times the cosine theta times the cosine of theta equals negative L omega squared times the sine of theta plus L alpha cosine theta. Isn't that lovely? And then AB is equal to Y double dot B, or YB double dot, which is equal to negative L theta dot squared times cosine theta minus L theta double dot times the sine of theta, which is equal to negative L omega squared cosine theta minus L alpha times the sine of theta. L alpha times the sine of theta. All right, that was a long one. So again, all I'm doing is tracing through the accelerations, finding their components, and transforming those via relationships we already know of alpha, omega, theta, etc., a combination of trigonometry and the equations of motion that we saw previously. All right, so we could look at another one of the double gear examples, but I think I'm good on that one. Okay, so let's see here. This here, and there are more examples in your text you could look at. All right, rate of change there, and so, well, I think I'm going to save this for next time, so maybe I can work through another example. All right. Okay, so let me think about this. So maybe I'll work through another example. And consider a system like this. Now, say we have something like this here. This is one you haven't seen before, I believe. A system of pins. That is free to move. So say we have this. This is going to be point A and point B here. And then, let's say we have point D down here. We have point D here. And then a distance down here, we have point E. We have point E. Now, then I'll give us some dimensions here, and we'll work through this. So let's say this is definitely not to scale, and this is 3 inches, and this is 8 inches. This is definitely not to scale. 8 inches, and this is 7 inches and 4 inches. Oh, that one's really bad. Kind of like that. 7 inches and 4 inches. So all of this is given, and also I know, knowing that the instant shown bar AB, that the instant that at the instant shown, let me say that knowing that at the instant shown, see, this is free to move. Like, this can rotate down and these can adjust accordingly. This is not a rigid frame. This is not a statics problem. The instant shown, bar AB has a constant angular velocity, of 4 radians per second clockwise. So it's actually going to go up like this. 4 radians per second clockwise. Determine the angular accelerations. The angular accelerations of bars, let's say BD and DE. So I'm just going to control this directly. Maybe I'll just do this by, I would just use it by hand or a motor or something like that. And I'm going to guarantee that AB will have a angular velocity, a constant angular velocity of 4 radians per second. And because these are joined together with it though, when I move this, the other two have to move. This thing's going to move, this thing has to rotate like this, so B has to come up and to the right. And then along a similar vein, D will have to move, although E will be stationary. Okay, so let's solve for that. In other words, we have a omega like this. Omega AB equals 4 radians per second. So let's work through this. Here. Here, well, actually, maybe I don't know if I want to go all the way through that one. That would be a problem that I would maybe issue as maybe a little bit of a challenge to you if you want to try this. Maybe I'll let you try this one at home if you wish. But the basic idea is that you will get, the first thing that you need to do is figure out that with a bit of algebra, you can find that the omega, the first thing is to realize you can find that the angular velocities of each of them, omega DE, is 2.55 radians per second clockwise, and omega AD is 0.955 radians per second. So that's something you can determine a little bit differently. And now we can apply relative accelerations. So I know that if I look at bar, consider bar, or just say consider bar AB, I can do the same sort of thing as before. I can say AB is equal to AA plus alpha AB cross R, B with respect to A, minus omega squared AB RBA. RA to B, you might say. And a few of these things are going to be 0. AA is going to be 0, there's no translation. And alpha AB is also equal to 0 because this is not, bar AB is moving at a constant angular velocity. So the only acceleration will be from the centripetal acceleration. AB is equal to negative omega squared AB times RBA, which is equal to negative 4 squared times negative 7i, and I will get that this comes to 112 inches per second squared I. Then if I look at now, so that's that. Now I can consider bar BD. Consider bar BD. And I can say next that AD is equal to AB plus alpha BD crossed into R D with respect to B, or from B to D, minus omega BD, the angular velocity of bar BD at that instant, squared, times R dB, again, the vector from B to D, and that is 112I plus alpha BD times alpha BDK crossed into negative 8j. Negative 8j. Actually, let me write that down here. I'm a bit out of room here. So that is equal again to 112i is my alpha b. 112i, or sorry, yes, 112i plus alpha bd times vector k crossed into negative 8j minus 0.95455 squared times negative 8j. And so AD, the absolute acceleration of D, so AD, the absolute acceleration of D, is 112 plus 8 ABD. So we don't have an exact value yet. ABD I plus 7.289 J. 7.289 J. Next, I will analyze bar DE, or consider bar DE. AD is equal to alpha DE cross R DE minus omega DE squared times R DE, or again, the vector from E to D, which is then equal to alpha DEK. This is in vector form, DE times K. And then the vector from D to E is going to be 11i, or sorry, from E to D is negative 11i plus 3j, negative 11i plus 3j, minus 2.5455 squared times negative 11i plus 3j, which is then equal to negative 11 alpha DE times j minus 3 alpha DEI plus 71.275i minus 19.439j. And so finally, at this level, I can say AD equals negative, if I combine this together, negative 3 alpha DE. So the overall acceleration AD is equal to negative 3 alpha DE plus 71.275i minus 11 alpha DE plus 19.439j. On the previous page from previously, I got that AD was equal to 112 plus 8 alpha BD times I plus 7.289, 289J. And I have AD, I have AD. I have two expressions of this. If you combine those together, basically equate components like components. Of AD, you can get the final answer that alpha DE equals negative 2.4298 radians per second squared, and alpha BD equals negative 4.1795. 4.1795 radians per second squared. All right, so that's one more long-form example for relative accelerations along a rigid body. All right, so we have a couple more major topics covered in Chapter 15, but I think we might save those for next Tuesday. So I think I might actually take the rare occasion and let you out early after all of the lovely computation we've been doing today. So, all right, I think that'll do it for today. I will see you on Tuesday. I'll put some homework up on the website soon. And as always, thank you.